Learning with big data. This is the final project work for ADTA 5900, and here we go. So the first section is going to be um, to explain a data set. So if you see here, this is going to be a Titanic data set. This is a disaster of like the disaster, the recovery, like how many people survived in the Titanic crash. Like we have two data sets here. One is the Titanic and Titanic 2. These are the two data frame which we have, and these two are considered as separate CSVs. So the actual image, it has number of images in the below Kaggle side. We have number of images which says like different methods, like it has number of classifications. So we would be using the convolutional neural network to make sure like we are identifying, reading those images, extracting those images, and classifying it based upon the character. Like those images, like those if we have two or three images, like we have to make sure like which of method of convolution is taken care, and which which pooling method is taken care, whether it's going to be maximum pooling or minimum pooling, and all the other equivalent performance initiatives which trains the model and provides a better accuracy. We will be considering those. So in this data we have it's a principle, it's like basically a source of data based upon the Titanic passengers, and the original source was given by Eaton and Haas in 1994, and the Patrick Stevens. This is the actual limited, which the company which gave us this information. And yeah, these data sets has different variables. One is the P class, survive name, age, home, destination, room ticket, both, and sex, whether he's a male or a female. And The P class refers to the passenger class, where they are segregated based on three: the first, second, and the third one. And there's a socio-economic class as well. So these are the abbreviations, like just sorry, descriptions about the variables used in dataset. So there are a number of the duplicate values were present in the source data. So we made sure like we are just going and removing those duplicates, and many missing edges for many missing edges, the new variables were also created. So that was the main intention of this one. Like we are just did some basic data cleansing activity to capture all the data set which is available on the internet. So after this one, if you go to this Kaggle website, you can just see the source data set and how it's being used. So here, as I told before, we have two data sets. One is going to be the training set CSV, and the next set of data is going to be a test set of data. So the training set data. So the training set data consists of the ground rules or the ground truth about each and every passenger. That the model features like a gender, class, and age, and it has quite innovative features as well. So in the other side, there's a test set of data where we don't give enough information about all the passengers. It's like the test data main job functionality would be like to predict the data values based upon the test data results. So the actual results is going to be present in the training set data, and the test set is going to be the predicted values, how the model is going to be trained and invoked for the way, in such a way like we get accuracy and accurate results, which is quite in sync with the actual training set data. So we have two sets here. That's the reason we have two sets here. So we are the Kaggle link. It also has a general submission CSV, which has certain predictions. Sorry, certain certain predictions based upon the passengers and their preferences. So consider like how the submission should look like. So this is one of the examples which was given. So this is depends on the each and every preferences of the passengers. So here I have just given the data dictionary of what and our columns were used here, like the ticket class were pay ticket class 1, 2, and 3, and sex, age of spouses, or number of children in Titanic, a fare place, and what's like a cabin number. Like it has three to four cabins. So we are just making sure like which cabin is coded. It's like a hot encoding style, like where we are going to assign a value to a variable parameter. So here in this variable nodes, we have a P class example for all the stuffs, like P first is going to be upper, 2 is going to be middle, and 3 is going to be a lower class. Um, and we have other variable description as well. There are siblings, parent, spouse, and number of children who traveled with nanny. All these important data values are available. So this valuable, as I said before, yes, this valuable would be two set data. So two set data, and one set is going to be the actual training data, and the second set is going to be the actual predicted data. And that prediction will vary based upon the accuracy and how we train the model. If we give a number of sample, like a large number of samples, and if the model is trained again and again, there's better chances to provide a better accuracy results percentage when compared to running it once. So that's all about the first part. The first part is it's this one. The first part is going to be to get dataset images or audio files. So the images are available on the Kaggle side. So we can just go and grab it out there. So the next one is going to be obtain the CFR data. Um, so for this, what we are going to do is like we have the Google stuff. So the Google GCP, on the GCP Google Cloud Console, we are just going and creating a part is going to be to build, train, and test the CFAR 10 data set on this will be on the GCP cloud platform. So what we are going to do is like on the previous step, we just there are around five data sets. So each around like each is the since the volume is quite big, so we are just splitting across into different data sets and uploading it into a cloud platform on GCP. So that would be inserted like as we said before. If you see here, um, let me zoom this one. So on the previous section, we have created a folder called JP underscore NTBK. That's the Jupyter notebook, and within that a new subfolder is created, CFR 10 dataset, and within that subfolder we have all the source data like that data batch 1, 2, 3, 4, and 5. So this would be having all the individual data sets, like it's going to be a combination like since the data set volume is quite big, since it has 60,000 images, we just wanted to make sure like we are going to split across into five different data sets and five different batches probably, and five different batches. So we are just splitting each batch. So each batch, when you upload into the like the Linux systems, it's gonna be like each file like data 1 to 5, it's going to be around 31 MB. So yeah, so we need to make sure since the volume is quite big, since it carries 60,000 images, so we just want to make sure like we provide the correct information, and in this file size, instead of loading instead of loading as just one single file, we can just make sure like we can just load across as multiple five different files. So that's what here I just mentioned. So it has 10,000 cases per batch. So each case, so it has 10,000 various cases. So we are just making sure like since if it runs on the cloud or on prem, there is chances like the TensorFlow going out of space, out of memory and out of space. So that's the reason we just wanted to make sure we are splitting across into five different data sets, and we are just feeding the data model, the Python or the Google CGP model. So here this one is going to be built and train data sets based upon the convolutional neural networks, and in order to feed the image, so each data it's given as image, so we don't have the actual data. So here the image is just considered as data. So how we are going to replicate those image and replicate in the sense like how we are going to train the model like to identify the image. That's going to be based upon categorizing what are the x-axis, the y-axis, the number of channel, height and width of the image. So it's like I can on the below sections I'll be explaining you the image width and all those things. But here let's go ahead and this is the formula. So the input tensor should be either width into height into number of channels, or number of channels into width into height. So this is the basic stuff. So based upon the number of channels we will be multiplying the width and the height, so that would give you the approximate image size. Like if you want to pixelize if you want to pixelize more on the image, you can do that. But initially we just want to make sure like we are just capturing the image, and the image is exactly identified, and the accuracy of image does matter, and the accuracy of the image it does play a key role in determining the type of model. So see, if you see here, this is the Python code for this training the model. So we have in the input data set we have number of data sources. Like if you see the number of it has images of aeroplanes, automobile, bird, cat, deer, dog, frog, and like various um, number of variables over here, and each will be assigned to a label. So and all the data batch it's getting assigned into a it's getting loaded into a model. So here, and this stuff is like we are having a row number, and that's the calculator. Like we have here the calculation is being done. If you see here, let me explain more clearly. So this is the image. Like if you consider a image, so the image needs to be reshaped. So first thing we are going to consider the value for data batch 1. From data batch 1, this is going to be an image, so we are just restructuring the image. So row vector, so that's the reason. So if you see the row vector of the image is exactly same as the number of elements. If you calculate 32 into 3 into 3, 3072, the count and the width of the row vector also will be like the same thing. um, First we need to reshape, and then we are going to transpose it. So first here we are just shown the reshape stuff. And if you see here, this is going to be the formula which I told earlier, which is going to provide the reshape and transpose the values of the variables, of the data. And the last one, and each plot image. So we are this one also is quite important. I am not attached the images. So if you see here, this is the data set for, sorry, if you see here, this is the model project work, which was for the CFR 10 data set. So I'm loading the file here. After loading it, probably what I'm doing is like I'm just assigning the values. So here it's going to be data batch 1, 2, 3, and 5. I'm just assigning all the parameters, all the values into the data batches. And here it has all the values which is available for the labels. And after this, we are transposing the shapes for each and every images. So this was the one I was showing, telling here, like each image, right? So this is the actual image. So for this image, we use matplotlib functionality to plot the image with the help of matplotlib. We be using that one, but the scalar in variables and whatever is required to identify, extract, or classify this image would be given by us. So if you see here, that's the thing, like we have different images, like so each images the value will be pixel values will be given by us, and based upon that the image will restructure. If you see here, like image will restructure and reshape based upon the values which we provide. So here, going back the stuff here, we are we are just doing a hot one code format. So the values, all the label values, different label values in the data set are being classified as zeros and ones to from zero all the integer values. So if you see here, this may be a better example to evaluate the hot and one hot encoded values for the label data available. So each the label data is given over here on this corner, and the index value is given over here. So it's going to be like for the value is index 0 to 9, and it's like zeros or ones. So the values of it's going to be yes or no, so it's going to be 0 or 1 information on the hot encoded data set. See, if you see here on the below example, we can see the x as a list of labels, and total number of elements in the list is equal to total number of samples of the batch. So it's like five. If there are five elements, so there are five samples in the batch. That what it means. And actually every single time one encode returns a two-dimensional tensor for, and it's directly proportional. That's like it's directly based upon the source row size and the number of columns that the image has. If the more the image has more column, more if the image has more columns, then more the complexity of data is. So that's like mutually exclusive. So it's tied up to each other, and they are on sync. So this is a code for training up the image. Here we are giving self-training images and labels. So here also, if you see here, we are just training the image, and the second part is going to be like the hot encode, like zeros and ones, and we are just giving looping into a batches. So it makes sure like the model is trained as well as the model is going to be hot encoded, like the value is being converted. So both the stuffs are taken care over here, and this is on a training image. So initially I told you, right, we are going to have two sets of image, two sets of data. So it's going to be training and the testing, right? So it's here we are just setting up a testing image. Here it's going to be a training image, and this is going to be a testing image. So we are just going doing the same thing, the test images and hot encode over here as well. So here we are going to perform the convolutional neural network with the input and the output layer. It has many hidden layers as well. We can add the activation function commonly known as ReLU layer, and it subsequently follows by the additional convolutions layer as well. In this example, we will be using a two-layer convolution layer solution for the section part 3. Okay, and here you go. This one is like quite straightforward, like because the first creation of the first convolution layer, it's gonna be here, and the input is going to be 5 cross 3 cross 32 matrix. So this is the input parameters you will be giving, and here if you check this one, like this is the first convolution part, right? So I'll just open the studio, Jupyter Studio here. Yeah, before that the image is feeded into the data stream, the convolution layer, using the cfar helper class. This class determines like whether all the trained batches, like are given as the input to the CFR class image class function. So this is just for setting up the training and the test image and the training image, which was discussed already. And after that, we are just printing whether all the images are set up right. And then here it's like these are additional supporting functions to initialize the weight, to initialize the bias, and to initialize the convolution layer. And when you come down, we have the placeholders which are created, like placeholder of x-axis and a placeholder of input. X is going to be the input data, and it's going to be a 2D array, and the y also is going to be a 2D array, and it's going to be a output data for h1. So if you see here, this is the next place where we use the um, a ReLU function to create the to reshape the placeholder. And as discussed before, like this part over here will determine the first convolution layer, and it performs the computation. The filter shape is like 5 cross the 5 cross 32, and the output filter also is going to be this of the same size. And if once the first convolution layer is created, then this pooling happens. Pooling is just to, as discussed before, pooling is just to decrease the spatial size of a picture to image the pixelite size. So if the image is being very big or very small, it's going to impact the recognition, how the image is going to be read by the system. So in order to make sure like the image is read properly, and the proper system, like proper pixelized size and proper spatial size needs to be determined and given over here. So this is going to be the second part. So let's go to the report once again. Yeah, so after this one, we in this example we do have, this is going to be a two-layer convolutional neural network. This one, the second layer is introduced because to decrease the spatial space of the image. um, so it's like we are splitting the image even for further. If it's going to be 32, now with the second iteration of the convolution layer will make the step as 64, like it's going to be exactly double, because it's going to split the data into even more minor chunks, small chunks, so is that it can fit over the screen more efficiently. That's the reason over here. And after that, we are just going with the TF session. Like this will be a fragment of each and every say, if each and every value, like step by step operation and execution for accuracy. So this one is the last accuracy check we do. For CIFAR data. And for a CIFAR 10, it comes, as discussed before, it comes like 5 separate batches. So we are just combining, we are 5 separate batches because each one is going to be 31 MB, and combining and loading it over a period of time, it will be a performance intensive operation. So we are just concerned on the performance as well. So here we are going to split the data and load it. And when we train the first iteration, this was for just a second. Yeah, this was for 5000 steps, 5000 steps iteration. And the first steps, it's going to be like initial step, it was like around 10.52 percentage, but we trained for accuracy more and more and more. The 5000 step came across up to 67 percentage. So it's coming up to 67 to 68%, 67 percentage of accuracy level. So this what is the maximum obtained, percentage level over here is going to be 60. For cipher data is going to be like around 67.01. Sorry, my bad. This is going to be I need to change this one. This one is going to be 67.01, because 94 was obtained for the MNIST data, and for this one it's going to be 67.01 percentage for the cipher data. And yeah, and that's it for the training module part 4. So when we part 3, sorry, and coming back to the part 4, part 4 is going to be the compare convolutional network performance. So here in this example we are going to consider the differences between the MNIST and the cipher data set. It's going to be a similar data set, not much difference, but we are going to perform two separate data sets, and the same convolutional method CNN is going to be incorporated on these two data sets. But here, we are going to do a comparative analysis. On doing that one, like this, um, sorry, on applying the spatial dimension, right? Like the pooling stuff, the pooling increases the spatial, it reduces the spatial dimension, as we know, the image distribution is more. So I will explain that in for coming session, coming steps as well. But here, pulling up and pulling down sample is responsible for the spatial and the size of the activation map. Activation map is what you told the images, like how big you can split across the images. So that's what we are explaining it as the activation type. And what it means, like, even though if you see, we saw for example, MNIST data was a single convolution layer, and safer data we have two convolution layer in place. That's the main example, because we have maximized the pooling. But that doesn't mean like we get better results every time we reduce the special results. The reason being, for example, I can just tell you with the accuracy. Like for MNIST provides accuracy value of 96.94 percentage while doing with a single convolution layer. But the cipher data, which has a max multi-level two layer pooling accuracy, gave us around 67.01. This states like MNIST provides a better accuracy results when compared to the Cipher 10 dataset, the convolution model. This tells us. This basically tells us, even though we increase the accuracy, or sorry, the pooling layer, it doesn't actually mean like we are going to get better results. So this, in the screen you can see like 96.94 is going to be MNIST, and 67.01 is going to be the mm, accuracy percentage of cipher data. So that's all for the part 4. Part 5. Part 5 is like improve the convolutional neural performance. This is what we are going to check over here. This effect of as I told you before, convolution layer, we are systematically applying filter image to create future maps, presence of those future inputs. So this is going to be a very effective and allows those input levels to learn low level. This low level features, that's the thing I was telling you about. It's going to be the granular level of the data. We are going to check for the granular level of the data, and if that doesn't match, even though we check for the granular level of data, that doesn't actually provide a good value. It can get further accurate by training the model again and again and again, but it depends on certain condition, like people should not think like always increasing the maximum pool value and reducing the spatial size will always provide a better results. So in this case, we are going to check with one more layer. Like initially we checked with two layer convolution. Now we are going to check with the three layer convolution. How this impacts the performance of the model. So here it is. So we can do various stuff like cropping, rotation, and shifting of the images based upon the matrix values. We can split matrix values, and we can just try sampling based on that one. But if you see here, this is the third layer pooling. So the third pool is also going to be of the same array size, 5 cross 32, and it has three options. And setting up the steps is going to be like cipher 10. Cipher 10, now we are going to increase the steps by around 10,000. So we are going to train even more further on the cipher data set. So now we are going to do like 10,000 steps increased, and we are going to add a third convolution layer. But on increasing to the third convolution layer, we see an increase from 67.01 to 68.01. That's a 1% difference. There is no much significant difference on the value, on the performance value when compared to the previous two-layer convolution network. This would tell like they apparently tell like we if we increase the convolutions also, um, it doesn't mean like we will be getting the good values. So this would get a in point better in point of time. Like if you train the model again and again, it will get better. So, and this is the project report. The project report. This is the CFA data set. So it has like around 100 classes, consists of 600 images and all those training images. So if you see here, as discussed before, like we this is all the various classes which is available on the image classes images which are available on the CFI dataset, and each image is going to be like 3 cross 32 cross 32 pixels long and pixels wide, which is going to be a value of RGB values, the red, green, and blue values. And it has like in convolution layers, and output channel is going to be 64 output channel. Each convolution is going to be 3 cross 3. All the image classification in the image time frame window, which was discussed before. Here, um, this is the concept of operation of a TensorFlow diagram. Like TensorFlow, we are going to check the strides. Like each image, we are just classifying it into a separate matrix. So each small boxes, it's going to be a spatial image. So this depends on the height, width of the channel, and the width of the image determines the convolution layer, like how accurate your values would be, or how clear the images pixelate with respect to the flow on training the flow. So it's like very common values over here to stride. It's going to be 1 comma 1 comma 1 or 1 comma 1 comma 2 in most of the use cases. Those values, it's going to be like over here the height. It's the these values are going to be the height, width, channel, and based on this one we are going to and the strides. So you can just compare all these things based upon this matrix value. And if we go forward, so this is what I told. This is the input. So convolution layer is the first layer. This is the matrix value, which initial spatial image we are doing, and we are doing pooling. So this one image is going to split across into multiple image over here, and this one image is one. This is a third layer of pooling we do here. So 1, 2, and 3. So we are just pulling and after this, once the image is getting very slow small, we are just going to flatten the structure into a matrix format here, and this would be a softmax or a relu format. This is going to be relu, and this is going to be a softmax where the values are going to be on 0 and 1s, like integer values. So this one will be transformed into an image, and this will be sent to a test model for training activities. So input image will pass to a series of convolution data pooling for F3 and up into a softmax function to classify the object for 0 and 1. So this is what I was telling, the value of 0 and 1s over here. So this is the figure of the um, image classifications. And pooling layers, see if you come here, this is going to be a pooling layer. The pooling layer is going to be like various parameters, partial parameters, and the spatial pooling is going to be a subsampling, which reduces the dimensionality. So there are three types of pooling: max pooling, average, and sum of pooling. Max pooling takes the largest element in the future map. This is the future map. Future map content is going to be like sum of, so the single depth, like, so future mass is like a single matrix. It's going to be summed up, and values are reduced into a 6 1 plus 1. it's going to be average value. So average value of it's going to be 1116. So it's going to be 6 here over here. And the average value is going to be two state. It's going to be sum of pooling over here. So it's like that. So we are just calculating the average value based upon the matrix over here. So this is for the average modeling and building the model. So building the model, we are capturing it as in two separate like ReLU functionality and softmax are being used, and we are using the categorical cross entropy for multiple multi-class classification problem, since everything carries on the same weight and structure is going to be the same. And training the evaluating the model, we see like this was the first model. This report is generated based upon the first model where we have um, the accuracy percentage of 67.01, and results will change based on the training patterns, and if you train over and over a period of time, but it will result in a good value. But it depends on the the polling size as discussed, and the spatial image pixel of the model which is being trained. And that's it for this presentation. Thank you and have a great day.